Hi, my name is Tanir Ozcelebi. I'm going to talk about some findings that we have from a piece of research that we did. We sort of started to investigate machine learning for intelligent lighting environments, and basically that got us to think about what actually these applications, in what ways these applications are different from other applications that you see around, other distributed applications even. So in many ways, the LED technology has allowed us to do many things. Apart from energy saving, you also see these effects about how you can control lighting better, how you can attach a simple control module that communicates with the environment and controls with light, controls light to support user activities. We keep talking about the intelligent lighting environments of the future, but I don't believe that many people actually realize what it actually means for the user. For many people, so this image is from the Boston University, and it's a very nice conceptual figure of what an intelligent lighting environment could look like. And many people think about the automation as the discriminating factor of future lighting environments. So what I mean by this is that I have an environment that decides on the desired lighting settings on behalf of the user, that thinks like a user, that decides for the user, that actuates for the user in an adaptive, context adaptive even way. In 1991, Mark Weiser wrote an article that's titled "The Computer for the 21st Century," and I'll just quote him. He said that so this inspired a lot of people that are working nowadays towards the realization of ubiquitous computing. The most profound technologies are those that disappear. They weave themselves into the everyday fabric of the fabric of everyday life until they are indistinguishable from it. So he suggests that applications should seamlessly support users. And by seamless, what he means, he explains in this sentence. He says, a good tool is an invisible tool. By invisible, I mean that the tool does not intrude on your consciousness. You focus on the task and not the tool. And for that reason, eyeglasses are a good tool. You look at the world and not the eyeglasses. You don't realize that they are there during the day. I didn't realize it until now I spoke about it. So it's good, but does this mean that ubiquitous computing means no interaction at all? So does this mean that we want systems that do not bother us and they just work? They provide us with services? I think no. I think that the future intelligent lighting environments are going to have even richer user interaction than today. So what we are after then is we are after context adaptive dynamic lighting that adapts its behavior to support human users. And for that, if we are going to also have user interaction, we would like to have an optimal balance between user interaction on the one side and control and automated control on the other side. So this optimal balance can be also personalized. You may have a different optimal balance than I do, because some people like to interact with the system and some people just don't want to be bothered by it. So the context, adaptation to context is apparently very important. We would like to, when we have a problem, given a problem, you see that people that are problem solvers, like engineers, gather together with the stakeholders They try to find out what they really need. They try to sort of draw a context around the problem. Drawing that context, defining that context is very important because it shrinks the problem space. That means you need much less effort, much less manpower to program something, for instance, solve a problem. So given this problem, we hope that we can define a context around it that is extensive enough so that it will work all the time. For instance, Apple warns their customers that your iPhone will only work properly between 0 centigrade degrees and 35 centigrade degrees. So if you take your phone outside on a cold night in Helsinki, if it's broken for that reason, its warranty is void. You cannot claim actually that it works. So, but it defines a context around the problem that you want to have a smartphone, and well, it actually helps the implementation. So, given enough time and effort, we have a development and implementation phase for a solution for the given problem in the given context. And this is typically, given enough time and effort, as I said, is quite doable for most of the problems that we have around. So as long as the problem remains within the context that is defined, users are happy. And the problem occurs when the original problem here depicted by the dragon, the problem context is actually broader than the context that was defined by the problem solvers. So if this context is not wide enough, if the issue that we are handling can be in a state that was not previously foreseen, then the system may fail. So the message that I'm trying to convey here is that the system functionality may be damaged if it's bound to a specific subcontext, especially when that context is not extensive enough. So the alternative to that would be systems that monitor context, that of course this monitoring will be limited by their sensing capabilities and maybe their communication capabilities. They learn from observed context and user interaction with the humans around them, and automatically adapt their services based on changing context. So like in an intelligent lighting environment that we keep dreaming about. So, for example, if you want to make a car that drives itself, this is disconnected from lighting a bit, but maybe just to give you an extreme example. If you want to make a car that drives itself, we have a context. We need to define a context around this problem, and that context probably has state information regarding all these things: roads, the road state, the state of the signs, the traffic signs, the traffic rules, the obedience of people that are actually driving around, and so on. And there are a lot of contextual information here. So as long as this state information regarding the things around traffic are extensive, very extensive, and they are accurate, we will probably have a car that drives itself. But the problem happens when, for instance, the drivers start not obeying the traffic rules. So if it's a software development project, the exceptions such as this one are probably handled, but that may also mean that the program just exits or is terminated. And it's not what you want here. You want, for different types of applications, user experience, user satisfaction, no matter what. So the learning definition according to Oxford Dictionary: the acquisition of knowledge or skills through study, experience of being taught. So we learn by experience. So the formal definition that I'm going to make here of machine learning: a process is said to be learning if its performance with respect to a given metric M, that metric depends on what you like the system to do, improves with experience over time. This is similar to actually the definition of Tom Mitchell. So is machine learning the winner then for this type of applications? It depends. It depends on the application specification, and the type of application that we are interested in here is intelligent lighting applications over distributed systems. Note that the distributed systems on which these lighting applications, intelligent lighting applications, are deployed are evolving over time. So this is a picture of what we have right now. Probably we have network technology, devices that are interconnected with communication protocol standards that can wireless communicate, and programming by experts. So we typically don't have a very nice API in this part of the figure. But what we are evolving towards is we want to have services beyond simple sensing and actuation. In here, what we have is typically programming to a fixed behavior, programming the system behavior to a fixed one. On the right-hand side, what we want is intelligent lighting systems that can adapt by themselves to changing contextual situations. Similarly, user interfaces are evolving. What we have today mostly is simple switches. They are mostly simple switches and dimmers. And in the future, what we are going to have is what I envision is that intuitive, tangible interfaces that you can even carry around with you, that is personalized to you. And when you enter a room such as this, it starts communicating to the room and gives you the lighting solution that you prefer. So this was earlier mentioned, and I think it's also a very nice user interface, the Philips Hue, and it's an example of such interfaces. So when we say machine learning, the general goal of machine learning is to, given some training data and a learning algorithm that's fed to the training data is fed to the learning algorithm, and our goal is to come up with a hypothesis as a function that maps future inputs to future outputs. So the input here can be any information like sensory data or any data that describes a context. And the outputs are the outputs that you would like to see from the application. So the classification accuracy in this case is defined and is used extensively as a performance metric, and the classification is said to be accurate if the this is a mistake. It's not input is not equal to output. Prediction is equal to desired output. Sorry about that. And we say that it is inaccurate otherwise. So we are in intelligent lighting. There is an interesting situation. Differently from many other applications, there may be multiple output light settings that are desirable for a given context. So, and we have randomness in the behavior of the users. So the true hypothesis may not be a one-to-one mapping. A given context can be mapped to multiple light settings that are desirable for the user. So in here, this lady says, I'm undecided between cool dimmed light and warm dimmed light. I like them both for my current activity. She just can't decide. So is it fair to expect that machine learning algorithm can decide something that even the human cannot decide. So there are inconsistencies in data sets generated by such a user. And all, even believe me when I say it, all our users that we tested with are like this. They cannot, given the same circumstances, they come up, their choices change, maybe based on the mood and so on. So we have randomness in user behaviors, and we have data inconsistencies. And I'd like to think that these are actually due to the fact that we are not able to capture the global context of the problem. It just requires too much effort, too much manpower, and maybe even then we cannot do that. So the best learning algorithm for intelligent lighting chooses outputs from the same distribution as a human user would. So the algorithm itself, the classifier based on such an algorithm itself, will have a random behavior, but we would like that its randomness is similar to the randomness of the user. It's not easy to achieve. We propose a relevance score as a quantitative measure of how relevant a prediction is. Just a couple of slides. And for a given state of the environment. So what we have here is for training data as inputs, we have user inputs, sensory data, desired outputs, and this is the training data, and you generate a hypothesis that does this. So what we see is that with classification accuracy, we have tested different learning algorithms. Actually, these were all supervised learning algorithms, and I can tell you that supervised learning, we found out that is maybe not the way to do this. For supervised learning, with different classifiers, you see here, the performance metric as classification accuracy is very low. Why? Because the classification accuracy gives you a binary score. It's either a 1 or a 0. When the system has chosen a light setting that is very much acceptable, but just not the light setting that is most preferable at the time, the classification gives a score of 0, and that gives you poor performance. We have defined another metric called the relevance score, which basically tries to measure how relevant a given output, given prediction is for the current situation. And there you see much higher scores, and which is also in compliance with user evaluations. When we ask users, they don't feel like this system performs here, they more feel like this system performs here. Of course, we need more analytical study of this. So, last remarks. Collecting data in such an environment is not easy. There are a lot of things that cause missing data. Some users don't have, for instance, smartphone interfaces. Some sensors will lose data. There are communication errors, therefore data will be lost again. So we need missing data treatment methods, and we need a combination of a specific treatment method and a specific classifier that gives the best performance. And we have some studies on that as well. Users must be able to select a desired light setting. Since the output is many dimensional, now we don't have a setting like this. We have many LEDs, and then we want that they do dynamic stuff. So interaction is different, and therefore the user interaction defines rewarding mechanism. For instance, for online learning, it's a good idea to work with user interaction designers, and that's what we do in the Intelligent Lighting Institute. And typical reinforcement learning solutions do not directly apply here, simply for the fact that in lighting, the next state is not necessarily a function of the action taken. Okay, I'd like to thank you for listening, and here are some references to some papers written by the people involved in this research. Thank you very much.